Okay, I suspect I will keep adding more and more to this course as more exciting and newer results keep coming. I don't know if it's exciting, it's often bad news. So let's add a little bit more to the extremes in terms of ocean heat waves, biogeochemical extremes, and what are called compound events, which also have been done on land, where you have earthquake, drought, or a flood, and then a pandemic. They all come together to make the situation impossible for the most vulnerable in most cases. So here is an example of ocean heat waves. So July 2020 ocean temperature anomalies, surface temperature anomalies, and this is the so-called blob, which has gotten a lot of attention, and we will look a little bit at that. And you can see that the western boundary current region here, the Gulf Stream area, got extreme events. The Arctic has made numerous records now. This year, in June 2021, I think it hit 100 degree Fahrenheit, which is just unbelievable. And these are warmer regions, and they are getting warmer, of course. Inland seas, Mediterranean, Black Sea, and is this the Caspian? Please check out. This region is critical as well because of the poor countries around the rim, plus the risk of cyclones and so on, and of course fisheries and so on get hammered as well, corals and so on. So marine heat wave impacts are listed like this schematically by Climate Central. We'll look at one example later on. Changes ranges of species habitats. So as warm waters expand, cold waters shrink. Tropical species may move northward, just like butterflies move north on land, and some plants move, but as we said, ecosystems don't move. Specific species, which are generalists, they're called mobile generalists, they can move, but there are some so-called sedentary specialists which are unable to move, so the species composition changes. The same thing happens in the ocean. Cold water species may get squeezed out because the range of cold water temperatures and regions of cold waters may shrink, are shrinking. Boosts tropical storms and hurricanes, as we already said, which has its own consequences on corals and also on land. Impacts of not just corals but all the related symbiotic systems. Impacts economics of fisheries. So obviously the catch per unit effort and the amount of investment. Already fisheries are heavily subsidized across the globe for all the countries. All the countries do it, and the price you pay for fish actually is less than what it actually costs if you did life cycle analysis. And of course it bleaches corals as well. Using the definitions we said before about heat waves in the ocean, we can look at the trends now. So global marine heat wave days for 1900 to 2016 have increased. The regionality, the spatial distribution makes for very important aspects as well, because there are productive regions and there are regions that are not so productive, so the impacts can be disproportionately high in some regions than others. But nonetheless, it is important to note how the marine heat wave days have jumped here. This is not good news, of course. Nice work from this group here. I think includes my good friend Alistair Hobday from Cairo, Tasmania in Australia. Marine heat waves occur everywhere in the ocean. So this is the 2003 Mediterranean Sea. 4 degrees C warmer than average for 30 days. Largest event on record. Mass mortality of marine fish in rocky reefs. That was disastrous. Normal heat waves can drive normal heat waves can drive marine heat waves by warming the ocean surface, which happens quite a bit. Air can warm very fast, but if it persists for the dynamic reasons of global warming, then it can begin to warm the ocean as well. Ocean currents can drive marine heat waves by moving around warm water, but remembering ocean currents move slowly. These days, the duration of above threshold temperatures on the ocean can be much longer because of that. So 30 days on land, typically you look for a threshold of 5 days. Right? Climate models, modes, sorry, like El Nino can cause marine heat waves, heat wave events to occur, which is natural variability, but now it is adding to global warming. This is what one has to watch out for. The 2011 Western Australia over 3 degrees C warmer than average for 60 days, largest event on record. Seaweeds, fish, and shark moved south. So as we said, the mobile generalists can move, but there are sedentary specialists who cannot move. So you can see this was a massive shift. This is the blob, 2013 to 2015, 2.5 degrees C warmer than average for 226 days. That is a very, very long heat wave. Longest event on record, caused unseasonably warm weather in the Pacific Northwest. Anything that lasts that long is going to affect weather and climate on land nearby. And of course into Canada as well. Here 2012 Northwest Atlantic, 2.5 degrees C warmer than average for 56 days, largest event on record. Lobster fisheries peaked early and led to Canada-USA economic tension. So you can see how the resource limitations, adverse impact on resources begin to affect socioeconomics and geopolitics, right? So there is always a big battle about who is catching which fish where, because the open ocean is a wild west where massive fishing happens because of few big countries like US, UK, Spain, Japan, China, and so on. Okay. So here is an example, regime shift from kelp forests to seaweed turfs after 2011 marine heat wave. So you can see the massive difference here. So kelp forests were dominating and seaweed turf was less from 2000 to 2009, and it shifted, and it's unclear when it will come back. So you can see the reef cover and the SST anomalies associated with these changes. So these are not just a joke. Impact-based indicators are always good, but if we have temperatures and we are observing things like this, where we are going from cool climate to warm climate, increasing extremes in both ends. So vulnerability, adaptation, the coping range matters. Here again, adaptation and vulnerability matters. So extreme events on both ends can happen, and with changing climate, we're going to reduce the cold extremes and increase the warm extremes. This is a real trend, but it's schematically shown here. Nikki Gruber's compound events and biogeochemical extremes basically looks at these sorts of things where anthropogenic CO2 is increasing, which is increasing atmospheric CO2, ocean acidity, and extremes. So single events are happening. Impacts cascade into organisms and ecosystems. So impacts on ecosystem services and human welfare, which begins to feed back to the impacts on organisms, fisheries pressures, pressure on corals, pressure on coastal ecosystems, mangroves, other things. Cascading effects happen throughout. Other effects, the atmospheric CO2 forces weather and climate modes and extremes. So there is natural variability, but also anthropogenic effect on ocean temperatures, circulation and stratification change, which changes the nutrient dynamics, primary production, secondary production, competition, species composition, and so on. So ocean acidification, well known. There are things that are not known. So the fronts, the vertical profiles, eddies, everything change. Fish and other species in water have evolved over time to spawn in certain regions, to grow in certain regions, to feed in certain regions, to senesce or die in other regions, and so on. So circulation and stratification changes are going to affect marine heat waves and going to create impacts on organisms and ecosystems. So ocean acidity extremes and heat waves then can create compound events. Similarly, circulation, stratification, warming, and ocean temperature changes affect also the low oxygen extremes, which again create compound events between heat waves and low oxygen, which you can see here. So this is the phase diagram of oxygen, acidification, and temperature changes. So you can see these here. pH change, temperature change, and reductions in oxygen, and they are shown here with multiple colors to indicate regions which have had multiple or compound events. So globally speaking, number of extreme days per year have increased from the 1880s. Number of extreme days per year in terms of pH swings have increased over time, and number of extreme days per year for temperature and oxygen, they are highly correlated because warming creates what is called deoxygenation because solubility goes up, but there are often changes in circulation which also contribute to deoxygenation and expansion of oxygen minimum zones and so on. And of course this is the number of extreme days per year for pH change. This is at 200 meter, this is at surface, this is at 200 meter. So oxygen below the surface is very critical for large number of species. Near the surface, photosynthesis happens. A lot of species live near the surface. A lot of them are able to dive and come back. Some of them are residents at different depths. For them, the oxygen distribution matters. As you know, oxygen is higher near the surface. We didn't look at the profile, but you can look up in my other courses or on Google. Photosynthesis and atmospheric exchange keeps oxygen high near the surface. Respiration and all the species draw down oxygen, so you get an oxygen minimum zone at about 1 kilometer, so oxygen drops off with depth, and that's why you look at something like 200 meters. So this is the blob that we mentioned, which happens here in the northwest corner, which has experienced one of the longest heat waves in the ocean. So when you look at over time, heat wave only, heat wave and low oxygen extremes, heat waves and ocean acidity extremes, heat wave, so then you can look at the triple compound extreme, and you can see that from 2013 or so to 2016 there have been massive triple compound extremes within the blob, which has well documented ecosystem impacts now from phytoplankton level to large fish in the ocean like salmon, which is very common in this region, and of course a lot of other ground fish as well. Okay, so this is an introduction which is in much more detail than the book, which aims at introductory levels, but I've kept it simple. I have not gone into the technical details of the papers and reports I'm using, so you can easily listen to these and get a sense of the impacts and the climate extremes. And as I said, climate extremes is a very vast field now, and there is a group which does attributions for almost all events, especially the big ones. It isn't always clear whether attribution really helps with anything. For example, saying hurricanes are getting intensified much more rapidly is useful. Attributing each hurricane intensification rates to global warming is useful to re-emphasize what the global warming is doing. How that translates to action is not always so clear. For example, if a region is getting increased incidences of hurricane hits or marine heat waves, like the blob in the northwest corner of the Pacific Ocean, northeast corner of the Pacific Ocean, northwest of US and Canada, then can you allot resources, can you do regulations, can you provide insurances and other socioeconomic actions and so on. So where does attribution fit into it is mostly the scientific curiosity to see exactly how increased greenhouse gases are cascading into humidity change, precipitation change, circulation change, hurricane changes, ocean temperature changes, acidification or pH changes, oxygen changes, and how together they form these compound events, and how compound events themselves are changing along the way as well. So let's leave this here for now, and I'm sure I'll be adding more as more interesting and important results become available. Okay,